6 tokens of code go in. 2 machine instructions come out. Something turned one into the other, and it wasn't a simple translation, it was 6 distinct steps. That's what a compiler does, and today I'm going to show you every one of them. By the end of this, you'll know exactly why your editor draws a red line under broken code before you've even hit compile, and why code you write by hand can end up slower than what the compiler quietly rewrites it into. A compiler is a pipeline. Each stage takes the output of the one before it, transforms it, and hands it off. Stage 1 is lexical analysis. The compiler reads your text character by character and groups it into tokens. Think of it like someone reading a sentence and marking where each word and punctuation mark starts and ends. They don't need to understand what the sentence means, just where each piece is and what kind of piece it is. In result equals a plus b asterisk 2, result is an identifier, equal sign is an operator, a and b are identifiers, plus and asterisk are operators, 2 is a number. White space and comments get thrown away. What's left is a clean list of tokens, but a list alone can't tell you the structure. A plus b asterisk 2 could mean a plus b asterisk 2 or a plus b asterisk 2. Resolving that needs the next stage. Syntax analysis, parsing, turns that flat list of tokens into a tree, called an AST, an abstract syntax tree. This exact pattern isn't unique to compilers. A database does the same thing with SQL. Text becomes tokens, tokens become a tree, and the tree becomes an execution plan. Watch what happens with a plus b asterisk 2. The parser knows multiplication binds tighter than addition, so b asterisk 2 gets grouped first. The plus node ends up with 2 branches, on one side and the whole b asterisk 2 on the other. Every language construct gets its own shape in the tree. An if becomes a node with a condition and a body. A function call becomes a node with a name and arguments. And when the structure is broken, the parser catches it immediately. Int x equals has an equal sign with nothing after it. The parser can't build a tree out of that, and reports a syntax error. That's the red squiggly line in your editor, before the code has even compiled. But a valid tree only proves the structure is correct, not that it makes sense. Int x equals backslash hello backslash has perfect syntax, a type, a name, a value. It just doesn't make sense to put a string in an integer. Semantic analysis is the stage that checks whether the program actually means something. Do the types match? Was every variable declared before it's used? Do the functions you're calling exist? The core of this is name resolution. When the compiler sees on line 2, it needs to know which a, where it was declared, what type it is. It looks that up in a symbol table, a structure that maps every name to what it represents. Every declaration adds an entry. Every use looks one up. Once the program is confirmed valid, the compiler needs to move it closer to the machine, but not all the way to machine code yet. First, it converts the tree into an intermediate representation, IR. The reason is combinatorial. There are many source languages and many processor architectures. Without a shared middle step, you'd need a separate translator for every language to architecture pair. With IR, each language only has to target IR once, and each architecture only has to translate IR once. Instead of n times m translators, you need n plus m. IR is also simpler than the original code. No operator precedence, no compound expressions, every step spelled out. A plus b asterisk 2 becomes 3 explicit instructions. Multiply b by 2 into a temporary, add a to that temporary, store the result. And that explicit simplified form is exactly what makes the next stage possible, optimization. The compiler looks for ways to make your code faster without changing what it produces. Constant folding is 1. If the compiler sees 2 plus 3, it already knows the answer is 5. No reason to compute that at runtime what's already known at compile time. Dead code elimination removes code that can never run, and if false block gets deleted entirely, never even reaching the binary. Loop unrolling takes a loop with a fixed number of iterations and writes the operations out in sequence, skipping the overhead of checking a condition and incrementing a counter every pass. Function inlining takes a small function that's called constantly and copies its body directly into the call site, skipping the cost of pushing and popping a stack frame. Modern compilers run hundreds of passes like these, which is why the readable code you actually wrote can run exactly as fast as hand-tuned code, sometimes faster, because the compiler sees optimizations a human wouldn't bother finding. The optimized result is still IR though. The last stage is code generation, where every IR instruction becomes a real machine instruction for the target architecture. And this is where one of the hardest problems in the whole pipeline shows up: register allocation. A CPU has a small number of registers, and they're extremely fast. The compiler has to decide which variables live in a register and which get pushed to memory. A variable used inside a loop stays in a register. A variable used once and never again can go to the stack. An assembler turns each instruction into raw bytes, and a linker stitches your code together with external libraries, resolves references, and produces the final executable, the file you actually double-click to run. Here's what changes once you actually know this pipeline. Every error message you've ever seen is just one specific stage catching a specific kind of problem. A syntax error means the parser couldn't build a tree, a missing parenthesis, a missing semicolon. A type error means semantic analysis found a mismatch, a string where a number was expected. An undefined variable means the symbol table has no entry for that name. But compiling isn't the only way to turn code into execution. A compiler translates the entire program before anything runs. You compile once, run it as many times as you want. An interpreter translates and executes line by line, in real time, instant to start, slower on every run. And there's a real middle ground. Java compiles to bytecode that runs on the JVM, which interprets it, but the moment it detects code running over and over, it compiles that hot path to native machine code. That's JIT, just-in-time compilation. V8, the engine behind JavaScript in Chrome and Node, does the same thing. It starts by interpreting, and once it spots a hot path, compiles it to native code on the fly. If you write JavaScript, you're already leaning on a compiler constantly without thinking about it. TypeScript compiles down to JavaScript. Babel transpiles new syntax into a form older browsers understand. Webpack resolves your modules and produces bundles. All three run the exact same pipeline underneath. Lexical analysis, syntax analysis, semantic analysis, transformation, output. There's a real cost to all that optimization though. It makes debugging an optimized build genuinely harder. Inlining means the function you set a breakpoint in might not exist as a separate call anymore. Dead code elimination means a variable you want to inspect may never have been kept around at all. The stack trace you're staring at can point at code that isn't organized the way you wrote it, because the compiler rearranged it for speed. That's exactly why debug builds turn most optimizations off. You're trading raw performance for a version of the program that still looks like the code you actually typed. So the next time a compiler throws an error at you, you now know exactly which stage caught it. Red squiggly line, missing bracket, that's the parser failing to build a tree. Type mismatch, that's semantic analysis catching an impossible operation. Undefined variable, that's a symbol table lookup coming up empty. You're not just getting an error anymore. You're getting a pointer to exactly where, in a 6-stage pipeline, your program stopped making sense. One more thing worth being precise about. The tokens in this video are not the tokens an LLM uses. Same word, two completely different pipelines. If you want to see what tokenization looks like on that side, and how a transformer turns those tokens into a working answer, that's exactly what the foundation of modern AI on this channel covers next.